Hello viewers, in this lecture I'll be teaching you about the molecular orbital theory, but this lecture would be only about the examples, the diagram representation. First of all, we should be known about some key points to just distinguish between the BMO, ABMO and larger energy and shorter energy. So first of all, the energy of BMO is less than ABMO. We all know that BMO is less energy, so that's why it's much stable. As written in second point, more bonds, more stability. That means the more the bonds will be, the more the stability will be, the more the strength would be. The more the bonds, the less the reactivity. The more the stability, the less the reactivity. The more the bonds, the less the energy due to stability. Like it is same as the second point, but the thing is that here the word energy is written. That means the more the valency it will have, the less the stability. The more the stability, the less the valency. In BMO, now that point is much like important point, that in BMO the density between the nucleus, while in ABMO the density is only the nucleus. Just suppose that we have two nuclei, a nucleus A and B. Now we know that in the BMO it has less energy, so the density will be like here. But in the ABMO the density will fly like apart from the nucleus because of the larger energy. Now that's written in this point. Okay, the atom is delocalized because of high energy, like most of the atom localized in ABMO. So because of higher energy, the atoms or the electrons localize. In the wave nature of the overlapping, like overlapping can be at the form of that dumbbells or circles. It can be in the wave nature also. So in the wave nature, the overlapping has more it will be like constructive and destructive overlapping, like from positive terminal to positive terminal and negative terminal to negative terminal. It would be constructive one. And if there is like positive terminal to negative terminal, so it would be the destructive overlapping. The more the overlapping, the less the energy, because all electrons would be stable. In a BMO there is constructive overlapping, in ABMO there is destructive overlapping. Like just suppose that an electron is like two electrons are clockwise. So if there is three electrons, it will be three electrons. So we know that in the ABMO or in the BMO we will place only two electrons, one like this, one like this, according to Hund's rule, and that one would be upper in the upper shell because of the higher energy anti-clockwise. So in that form the ABMO will be held in destructive overlapping, and in BMO there will be constructive overlapping. Let's move forward. Now in this figure you can see that the structure. First of all, what we have to do, I have just written whole steps in my previous lectures. So if you want to learn all the basics, I'll give the link in the description. Just watch that video. It will be clear to you all the rules. First of all, we will just draw these lines. Let me just write it first. Okay, after that we will draw these lines. These lines will just show us that is it ABMO or BMO. Third one, we will place the electrons here. Like we will place that the x-axis, electrons in x-axis, and electron in y-axis, electron in z-axis. Now here one thing should be clear to you all, that x-axis is cause sigma bond, so it's different. But in the y and z axis there is pi bond. Y and z are pretty equal to each other, so we always write as, apart from that, if we are talking about the y and z axis, so we will write it combinedly. So here in this lecture or in this example, I have written just H. So we know that in H there is one electron, so it will be 1s1. Now here I had written 1 as 1 and here I had written 1 as 1. Now there is one atomic orbital and here is the second atomic orbital. So by that, what we'll do next? First fill the atom that has less energy. So first we'll fill BMO. If there is 3 electrons, so then we'll fill in the ABMO. But here we have only 2 electrons, so we will fill it in the BMO. And we will find that there is sigma bond between it because it is in y-axis. But if we're talking about the ABMO, there would be a star to show that it has higher energy or it is an ABMO. Let's move. Oh, sorry. I forgot to find the bond energy. Now to find the bond energy, we will subtract BMO from the ABMO. Now here we know that then the BMO there is 2 electron and in the ABMO there is 0 electron. So 0 minus 2 would be 2 divided by 2. Here it is written. And 2 divided by 2 is equal to 1. Now it means that we have valency in ABMO or it only has single covalent bond. Let's move to second example. Now let's talk about oxygen. Now I have divided the oxygen in 3 parts. First of all, we know that S shell or K shell. Then like this, in this it is K shell. And let me just change the color of that marker. Okay, now these all are L shell. So it should be clear that I have written these apart. Now this is also in x-axis. This is also in x-axis. So this would be written apart, but these all would be written combinedly. Now let's talk about 1s2. Now 1s2 and 1s2. Now we have 4 electrons here. Now to fill 4 electrons, first we will go to BMO. We will fill 2 electrons in BMO and after that in ABMO. Now to find bond energy, we will minus BMO from the ABMO. Now it will be 1 minus 1 and 1 minus 1 or 2 minus 2 is equal to 0. So 0 divided by 2 is equal to 0 because its answer would be infinity. Now this is second part. So in this like I am talking about this one. So in this one we will have of course 4 electrons. So the configuration would be same. 4 electrons, 2 electrons in BMO, 2 electrons in ABMO. Now here we'll minus 2 by 2 and then after that we'll get the answer 0 because there is no valency. In the third part we have like I have talking about these all. So in these all there is a valency of like let me just show you that there would be first clockwise, clockwise, clockwise. Then after that anti-clockwise. Clockwise, clockwise, clockwise and anti-clockwise. Now in the K shell we'll be having like combinedly. I'm talking about all these combinedly. So in the K shell we'll be having 6 electrons because combinedly oxygen has 8 electrons, so it would be written like that. So in this configuration I will place this px here and this px here. So combinedly there would be 8 electrons. So first of all we'll just fill BMO. In the BMO there would be like first in the lower case and second in the upper case. Now I'm talking about the upper case because we know that there would be a combined system and it's in the x-axis, like px is in the x-axis. So it will be written apart and py is equal to pz because both of them have pi bond, so it will be written here. And after filling this all, 6 electron would be minus. Now 8 minus 6 would be is equal to 2. So to fill 2 electrons we'll go to first less energy one. We know that less energy is in pi bond here, so we'll fill that and after that we'll be having that bond energy 10 minus 6. Now here 10 means that we have 8 electrons here, 4 electrons here, 4 electrons here, and 2 electrons of 1s2. So after that we'll be 2 electrons of the at 2s2. So after that we'll be having answer of 4 divided by 2. 4 divided by 2 is equal to 2. And that's all about today's lecture. Bye bye.